Hello everybody, welcome to my next video today. Today we're gonna talk about the DMA as promised before. We're gonna show you how the DMA works on the ADC example. What the DMA is, it's a direct memory access controller. This is a peripheral inside your microcontrollers that copies data from one part of the memory to another, or from a peripheral to memory and vice versa. This is very useful because we can use the DMA to automatically copy bits of data instead of using CPU for it. That way we can use CPU for other more important tasks. So, the ADC part is very important because we only have a few actual ADCs. As you remember from before, we can go to the datasheet for our CPU in this case, scroll down to the ADC, here it is, and we can see that there are only 3 ADCs, but we have multiple pins. That's because each ADC has a multiplexer, so it can select from which pin it is reading. That way, if we multiplex through multiple pins at very fast speed, we can simulate or we can pretend that we're reading from multiple pins at once, but by reading one after another in a controlled sequence and then knowing which reading is for which pin. In Arduino we only used analog read and that did everything automatically, but now we have to do this from scratch. So if you read from more than one pin, we have to use some kind of memory copying from our data register, from our ADC, so the new value from another pin can arrive into that register before it gets overwritten. That's why we will use the DMA to do that for us. So, if we begin, let's go into our reference manual. We have multiple DMAs in this case for our processor. In our case 2. So let's go to the DMA section to learn more about it. Here it is. We have 2 DMAs and each DMA has multiple channels from which we can read, and the channels control from which stream the data comes inside the DMA. So the channel is configured for the global DMA, and then the stream is where the data actually comes inside. So here we can see that each DMA controller has 8 channels and 8 streams. If we go down to a graph, here it is, this is the channel selection. So here you can see this is the data that comes into the DMA, and here are multiple streams called stream X from 0 to channel 7. And with channel select, we select which stream we want to use. So on the streams here, vertically, here comes the data, different kinds of data, SPI, UART, I2C, timers, and whatnot. So this is the data that comes on each stream. And we can choose each channel to choose the correct peripheral we want to have it's connected to. So this is the basic diagram for a multiplexer. And as you can see, where is the ADC that we want to use? On the DMA2. Here's this. The ADC1 is connected to the stream 0 and stream 4. We're going to use the stream 4, but what's important is also the channel. So this is on the channel 0 selection. This is going to be important for later. So let's go back to our code. This is the code that is exactly the same as before, so you should be able to follow along with no problem. For the beginning, let's just delete some stuff and I'm gonna explain why. So let's just empty our while loop so we have everything clean from the beginning. For the first part of this example, we're just gonna copy using DMA only one value from the ADC, and that is the potentiometer that I have on the breadboard. So this is gonna do exactly the same as we did before with the CPU, but now we're gonna use the DMA so the CPU can just stick around and do whatever it wants. First, let's go to a function. So let's go to the function called Adc Get Conversion Value. Oh, it's in here. Here it is. So this is the function that returns our conversion. What it actually does, it just initiates this function, which is that it requests from a particular ADC the data from the data register. This is also going to be important. We have to know from where inside the peripheral we want to read the data. Let's go back. We have to firstly initiate the DMA. As you might have guessed, the first step is the clock. So let's go to the rcc.c file, which is here, and let's search for DMA. In our case, we know that we want DMA 2. And here you can see that both DMA peripherals can be initialized with AHB1 peripheral clock command. Let's copy this one. And let's close this one for now, and let's just close this one. We already have the AHB1 clock for all of the GPIOs, so we can just add this one right over here. Great. We have the clock. Now we need some kind of structure, as with all other things. So let's just create another function for the setup. Let's call it DMA2 in our case. DMA2 setup. Let's also copy it here, so it's the setup is initiated in the beginning, and let's put it right behind the ADC. First is some kind of structure. Let's go into dma.c file, scroll down, and we already see the dma dinit function. This is not our structure, but this is the definition of which DMA and stream we want to configure. Here we can see the DMA y can be either 1 or 2. This is the DMA 1 or 2, and the stream 0 to 7. So there are 8 streams. What we want is here it is, the structure initialization. Let's do it as before, just remove the asterisk, and here is the init structure. Let's scroll down to the struct init. Here is the initialization of default values, so let's just copy this. And let's go through all of them. First is the channel member, as you remember, channel 0 for ADC1 and stream 0. So this can be left default. Next is the peripheral base address member. Here we have to put in the address from which we want to read, from the peripheral side. So as we know before, if we want to read the data from the data register, we have to use this command, ADC1 in our case, dr. So this is going to return the value from the data register. If you put this sign and before it, this is going to return the address of this data register. You can also go into the register table and find it and calculate it by yourself. I had fun with that as well and got the same number, but it's not worth it. This is just a shorter and tells the story of what this command does. So this is where we grab the data from. Now you need to know where to put the data into the memory. In our case, let's just make it a 16-bit, so it's all a little bit simpler for the proof of concept for now. So this is the global variable. It has to be global, so it can be accessed all the time by all code. So the memory is allocated for it in the beginning. So this is the ADC data. So we want to copy its name. And then as well as before on the upper function, put end here. So we put in the address of this variable, so where it's stored. Next is DMA dir. We can go to the dma.h file, search for it so we know what we can put it. It says specify the data will be transferred to memory to peripheral, from memory to memory, or from peripheral to memory. We want the peripheral to memory, so let's just scroll a bit further. And here are all the options. We want to copy it from the peripheral, so this is the ADC, to memory. So this is the default version, so we're just gonna keep this. Next is the Dma Buffer Size. Let's search for this one. This specifies the buffer size in data unit. So this is not how big is the data, but in the data unit, that means how many data units. So in our case, it's only gonna be one 16-bit data. And if you have to read 3 of them, you will want to put 3 in them, or 100 data units, 100. So in our case, 1, because we're only gonna copy 1 data unit. Next is the peripheral inc. This is the function that is gonna increment the address of our peripheral. So we start with this address, and if this is enabled, it's gonna increment. But we don't want to use that because our data register is on the same address all the time. So we leave this disabled. But if we want to use this for an array, and array is just multiple values like this, You can use it, you can simplify it by, here is a more straightforward, so it's vertically, so it's like memory addresses, so it's like vertically, and this is address, let's say 1, this is 2, this is 3, this is 4. The name of your array, so if this name of this array is called ha, this name of this address points to the first value or the address of the first. So this is automatically a pointer to the first one. And if you want to copy data inside here and then inside here and then inside here, we want to enable the memory incrementing function, so it does that automatically for us, so we don't have to do that ourselves. So this is useful when using an array. But now we're just using a single variable, so this can also be left disabled, but we will enable this later. Then is a data size member. This specifies the size that is gonna copy. If we go down, we can see the word, half word, and byte. Word is a term for a 32-bit, half word is 16, and byte is 8. We want to use half word because, as we know, we can go back to the adc.c file. It's only going to be a 16-bit number because the first 32-bit, if you remember from the previous video, if not, go check it out. In the previous video we saw that the first 16-bit of the data register for the ADC is reserved and only the letter 16 are to use, and only 12 of those is at the actual number. So you want to use half word. Also, with the memory data size, so we want to put it into a how large, we want to put it in also a half word size, because we have a 16-bit. If you would have a 32-bit variable, this would also work, because it's gonna fill it up from the least significant digit upward. So it's gonna fill the first 16-bit and leave the other 16 untouched. Next is the Dma mode. We can, nope, not this one, this one. Here it is. Let's search for Dma mode. There are two: normal, which is just gonna copy each one and then stop, and circular. This means it's gonna do it over and over and over and over again. We can see this from here, continuous conversion mode. This is gonna do it over and over and over again without us telling it to start a new one. This is kind of the same, you can imagine it like that. So we want to put it in the circular, so it's gonna do that as the ADC converts over and over and over again. The Dma is gonna copy the data over and over and over again. This can be optimized, but this is just a crude example. We have all the power in the world and no optimization for now. Next is the priority. We can keep it, oh, here it is. We can put it into medium, so it's gonna do its job properly. But if the data is really crucial and you have to copy the data before other data, if you have multiple Dma controllers or multiple data being copied by Dma, you can use this to specify which data gets copied before others. So you have to reserve very high for really those that are very important. So you can leave this the low, or you just use medium for safeness. The next are gonna be defaulted. You can go back here. The priority is, as we said, medium. The FIFO mode member is gonna be disabled, and the threshold, we don't want to mess anything with FIFO. The memory burst will be a single one, but we have multiple options. We have 4 different options, but for our case we're gonna use just the single one. Yours may vary, that's why you need to research what type of work you need to do. Next is the peripheral burst, and this is also gonna be single, so it's gonna do it a single time. So this is everything actually. So let's just delete this. And before I jinx myself, don't forget to replace this with dots, because this is a structure, not a pointer. Now we need to initialize it. Let's delete this and go up where there's the Dma init function. I just copied the whole function. And we need to specify from which Dma and stream we want to enable it. We know we want Dma 2 and the stream, in our case, 0 or 4. This would be good. Next is the structure. We need to, as the asterisk says, pointer to a structure. So let's do that. This is the same one as this one. And now we just need to initialize. Like with ADC, we have configured how it will work. Now we need to start it. So this is the Dma Command Function right over here. So you can put in here and copy this. This is the same, and the new state will be enabled. So this is all. This is gonna set up the DMA and start the DMA. Let's just check with ADC what the ADC will do. ADC is still gonna read from channel 0 and then channel 1. But we need to have the ADC, when it stops the conversion, tell the DMA, here I have the data ready, convert it. So if you go to the adc.c file and, oh, here it is. Oh, how lovely. Regular channels DMA configuration functions. So as it says, the Dma mode is enabled after each conversion of regular channel, a Dma request is generated. This is great because the ADC is gonna tell the Dma, hey, convert, here's the value ready, come and get it and copy it. So here we have a Dma command, so this is gonna enable it, so we can use this function. I just do it before the initialization of ADC. And we want to do this for ADC1, and the new state is enabled. Also, we want to use this function, enables or disables the ADC DMA request after last transfer. So when it's transferred, the function is gonna call the DMA. So this, we can copy this function. So when a conversion is done, this is gonna call the DMA to do its job. So I'll just copy this and enable it. We enable the ADC and start conversions. Great. So if you just leave it like this, our ADC is gonna keep converting in the background and the DMA is gonna copy the data. Let's just present this data over usart. So let's just gonna use usart. Our function is usart send number, and we're gonna send the ADC data, and let's just send a new line command, so the data will be readable. This is /n, and then let's just put a little for loop so we can waste some. This is inefficient, but the DMA is doing it in the background, so we don't need to rely on the CPU to copy the data from ADC to memory. So you can use the I is less than system core clock. This is a global variable divided by 30. This is roughly 2 or 1 a second. I plus plus, and then execute the function NOP. This is just an empty function, so our compiler just doesn't ignore it. Save it all. Go into a make file. Make sure you have the correct address for your username, and let's also include the DMA. So it's gonna compile the DMA as well. Save it. Let's open a terminal and run make to see if it works. And we have some warnings. We have a warning because the base address, because the addresses are in 32-bit, because this is a 32-bit microcontrollers, all the registers are 32-bit, but we're inserting a 16-bit register and a 16-bit part of register, and we're inserting the 16-bit variable because the variable is only 16-bit. So to avoid this error, so it's all a little nicer, we can put in uint 32t. So this is gonna convert this into the 32-bit number. So I'm just gonna copy this one here as well, and let's run make again. We have no problems. Let's run make burn. It's gonna copy it up, and let's open our terminal. And it's quite slow, but we can do anything we want about it. No problem. Let's just change it to 100. So it's gonna be a bit faster, no problem. Here it is. And I'm gonna turn the potentiometer, and you can see the data is changing. So you can see that the DMA is doing its job and the ADC is converting. So this is working no problem. I see the 20 minutes. Oh, this is fast. Because this is the point, I want to stretch this video a little bit so I can show you how we can read from multiple pins and how that's done. Let's go back. I'm lazy, so I don't want to go to grab another potentiometer, but my microcontroller got my back. There's a temperature sensor inside it, so let's go look after it. Let's go in here. Oh, how convenient, temperature sensor. That's a temperature sensor inside this microcontroller, and it says it's connected to the ADC input 16. Great. Let's go here, back to the ADC, and with regular channel config, we know that we config this one, which channel we want to connect to the ADC. So let's connect to channel 16. If you want to know what this is for, let's go back to the ADC.c, not .h, and we want to search for temp, and here we can see the declarations. The channel temperature sensor is ADC channel 16, so we can use also this declaration because it's gonna use this one, and then with this one it's gonna use this number and so forward. So this is just for make it readable, so you know it's the temperature sensor. Next, with temperature sensor we have to enable it so the temperature sensor works. So let's search for temp. Where are you? Oh, in this section. Here it is, the temperature sensor and voltage reference init command. So this enables or disables the temperature sensor and VREF channel. So this is gonna enable it on the channel. So let's do it before the command. So no problem here. The new state is gonna be enabled. So this is gonna enable the temperature sensor after the channels have been configured. Next, we have now two channels. So number of conversion equals 2. Second thing, the ADC needs to convert the first and add the second, the first and the second. That's why we initiate the scan conversion mode. If you remember, we had this disabled, but now we want to enable it, so it's gonna cycle between those two channels. Another thing, this number here, we saw it, this is called the rank. This is which channel is gonna get converted in which order. So this is gonna be converted first, and this, let's do it second. We cannot have it on the same number. So it's gonna first convert our potentiometer, then the temperature sensor. This is all we need for the temperature sensor. Next, we need to stick two values somewhere. So let's convert our ADC data into an array. So it's gonna be an array called ADC data 2. Next, this can be like this as well, because now ADC data as a name is already a pointer to the memory location. This is okay, channel is still okay. Next, buffer size. Now we have two packets. We have the first conversion and the second conversion. Have this enabled. Memory inc, we have to enable this one, so it's gonna start with the pot. Yeah, thanks. Potentiometer. And then is the temperature sensor. So this is the array. It's gonna be one data, and the next memory location is the next data. So we want for our DMA to automatically go forward, and then when it's only 2, it's gonna go back to the pot. So let's delete this and enable peripheral inc. No, the memory one. Enable. Yeah, spelling. Yeah, this is correct. Everything stays the same. And now we read it, and the DMA is gonna do this. Okay, the ADC converts the first one, the ADC is gonna read it and put it in the memory location ADC data. It's gonna increment its time number. Then we're gonna read the second one, hey, DMA copy it, and it's not the second one, and gonna put it into the ADC, the second part of this array, and over and over and over like that. So let's send those numbers 2 times. So let's put a tab, this is /t, and now we have to specify which one. So let's first use 0 for the first one and 1 for the second one. So this is gonna be the potentiometer, and this is gonna be the temperature sensor. I know it's not in degrees Celsius, but let's just test if this works. We're gonna burn that, and let's see what we get. Brilliant. We have potentiometer still changing here as I'm turning it. And here we have a temperature sensor, which is kind of stable. So let's see how we can read some useful information from it. Let's go here, search for temperature, Yeah, whatever. Oh, maybe. No. Where are you? Temperature sensor. I know where this is, but on the video I have to do everything as you would search, so the dumbness. Oh, here it is. This is the temperature sensor characteristic. This is what we need. There are multiple things required to calculate our temperature, and here are the characteristics that we want to use. This is the slope. The slope is said it's linear for the whole temperature range. So this is the slope, the millivolts per degree Celsius that is gonna change, and we need to have a reference voltage for the temperature at 25 degrees Celsius. Let's go to our reference manual and search here for the same thing. You have to kind of jump between the reference manual and the data sheet to know what you find anything. So here we says the temperature sensor is connected to the IN16. That is useful, but we already know that. We need further information. Temperature sensor. Is this what we want? Yes, this is what we want. Here is the temperature sensor. We enable it with that enable command, and it's connected to input 16. And here's the formula that we need. So this is the voltage that is gonna be read minus the voltage at 25 degrees Celsius. This is this one. Then we're gonna divide it by the slope, so we convert the volts divided by millivolts per degree Celsius. The volts cancel, so the degree Celsius, and we add back the 25 degrees Celsius. So let's do that. So let's copy this function here. Let's firstly do a float temp. This is gonna be just a quick one. That's gonna do temp equals the ADC data 1, and this is gonna be the temp, but we want to send it as a 16-bit. It's gonna convert it. Well, we will have some losses, but this is the quickest way. The temperature is gonna be this number. If you remember to convert it to volts, multiply it by reference voltage and divide it by the resolution, which is 12 bits. So in this case it's 1 shifted left by 12 places minus 1. This is volts. So this is this. Now I have to remove this number at 25 degrees, which is 0.76 volts. So let's do temp minus equals. This is the fast one, so we remove 0.76. Next, let's do it in steps, it's easier. We're gonna divide it by the slope, which is 2.5 millivolts per degree Celsius. We have it in volts, so it's dividing by 0.0025, and then we have to multiply it. Wait, talking out of my rear. We have to add the 25 degrees back. So let's just do temp plus equals 25. So we convert it to volts. We convert it to temperature and send that. Let's save this. Let's see if this is okay. It looks like. Let's burn it and look at the result. Strange. Well, this shows that I had this error before. The temperature should be somewhere around 30 or so. And the funny thing is that if we comment this out and upload it again, the temperature is something that it should be. Let me see if I put my finger directly on the CPU. You can see that the number rose from 31 degrees now to 35. Come on, 36, yeah, we got 36. So it works. So I don't know about that, why this works. I used another STM32 CPU in the past, and this formula, including the plus 25, worked, but I don't know why it doesn't work now. If anybody knows, please comment. down below. But here you can see it works. So the DMA is copying the data from the ADC in the right order and displaying it here on our serial terminal. And we can still change the potentiometer value. Great. So thank you for watching my video, for sticking that long. So I hope you now understand roughly how the DMA works, what it's used for, and for all the makers that mostly use ADC, this is the saving grace, that it's gonna help you use the ADC multiple channels and not just stuck with one. So thank you. If you have any questions, post them down below, and we'll see you next time.